So last time I left you with a cliffhanger. We talked about this, that every monad can be obtained from an adjunction, and I started talking about this adjunction. I defined this adjunction. There is a pair of functors. There is a category of monad algebras, the Eilenberg Moore category, right? The EM, or also called CT, where T is the monad, right? C is the category in which this is an endofunctor. And we have an adjunction between C and CT. There is a forgetful functor UT, and there's a free functor FT, right? So the forgetful functor just takes any algebra. So an object in CT is an algebra. So it's it's a carrier A and some evaluator sigma. And the forgetful functor just forgets about sigma and just maps it to A, which is an object in category C. The free functor, on the other hand, has to take an object from C and create an algebra in CT. But it has to be an algebra that's also compatible with our monad, T. And it turns out that we can easily, if T is a monad, then we can create this from A, from an object A. We can map it to an algebra TA. So TA would be the carrier for this algebra, and the evaluator would be mu A, because the evaluator goes from TA down to TA. So this is mu A, right? So an algebra, a monad really contains this like huge family of algebras there, right? It's just funny algebras because they don't really evaluate anything. Strictly speaking, they just like smoosh together things, right? Using mu, using join, right? So we have a pair of functors. And I think last time I showed you that these functors actually form an adjunction. So this adjunction was defined using unit and co-unit, two natural transformations, right? So unit eta t, which we figured out we can define as simply the natural transformation eta from our monad, the unit of our monad. So the unit of adjunction here happens to be the unit of the monad, right? We can choose it this way, and it works nice. For epsilon, we chose this. Epsilon has to go from the category of algebras back to the category of algebras. So it takes an algebra and actually picks the evaluator for this algebra. The evaluator of this algebra turns out to be also an algebra morphism. Okay? So if the evaluator for the algebra is compatible with the monad, that's the important part. Because normally an evaluator of an algebra is not an algebra morphism. But if it's compatible with monad, then it becomes also an algebra morphism between these monad algebras. Okay? So this is why it works. So epsilon acting on a sigma just gives you sigma. So it's sort of like a forgetful thing, but it forgets the other thing, right? So the forgetful functor was forgetting about sigma, and this co-unit of the adjunction forgets about the object. It just gives the sigma. Okay, so what I want to show you is that these two functors, this pair of functors, well, a pair of adjoint functors always define a monad. A monad that's defined as U after F, or right after left functor in the adjunction, right? So that's the monad T. So in our case, this will be UT and FT, right? These special two functors. And let's see. So this is the monad that's generated by the adjunction. And I want to tell you that this monad that's generated by the adjunction is actually the same monad that we started with, by miracle, okay? So let's see. So first of all, how does this work on objects? Well, the free functor, right? It will turn some A. So when acting on A, right? F acting on A will give us this algebra TA mu A, right? This one. So that's the F. Now we are acting with a forgetful functor on this, so we'll just forget mu, and we end up with TA. Hooray! It worked, right? So this monad that's generated by UF is actually the same monad we started with. Now, the unit of this monad, UF, right, this epsilon T, is actually the unit of the adjunction as well. So when you have an adjunction, the monad that's generated by it uses its unit as its unit, okay? So it's like all the same unit. And this unit also is equal to the original unit. So the original unit, same as the unit of the adjunction, and same as the unit of the monad that is generated by this adjunction. So full circle. It's the same unit. So finally, the final thing is, what's the multiplication, the mu, that's defined by this adjunction, right? So mu is defined as, for an adjunction, is defined as the horizontal composition of, or whiskering of epsilon, the co-unit, with F on the right and U on the left, right? So this is like these are functors, this is a natural transformation, so this is like a whiskering of this natural transformation between two functors. Right? So if we look at this, well, so how does it work? The F free functor, what does it do? Well, it generates this algebra, TA mu A. Epsilon, as we said, forgets about the object and just keeps the evaluator. So the evaluator is mu A, okay? And the forgetful functor, when it's acting on morphisms, it's identity on morphisms, right? And forgetful functor forgets about structure, but it keeps the morphisms. So this is actually equal to mu, the original mu. So everything works nicely, okay? So to summarize, right? We have an adjunction. We started with a monad. We generated an Eilenberg Moore category of monad algebras for this monad. Then we created this pair of functors. We showed that they are adjoint to each other, and a pair of adjoint functors generates a monad. And we found out that this monad is generated by these two functors is the original monad. Okay? So what that shows is that not only every pair of adjoint functors generates a monad, but also every monad generates a pair of adjoint functors that generates this monad. So there's like correspondence between monads and adjoint functors. It's not a one-to-one correspondence, okay? I just showed you one possible adjunction that generates this monad. There are many more, possibly many more adjunctions that generate the same monad. One of them is generated by the Kleisli category. But I'm not going to go into it. You can find it in my blog. And now for something completely different. Although not really completely different, because we are still talking about algebras and monads. But there is a different take on algebras that's maybe more in the spirit of, I don't know, high school algebras, right? It's like when you first learn algebra, it's defined in terms of operators, right? Now, when I defined an algebra, I was talking about F algebras. You start with an endofunctor, and you define an algebra as an evaluator. It is a carrier and an evaluator for this functor. But this functor usually has, in most examples, and in particular the example of a monoid, this functor has a very simple form. Okay, this functor for a monoid has the form. Well, let me write it symbolically as 1 f acting on A is 1 plus A times A. Okay. What does it mean? Okay, this is like a familiar notation, but it means something totally different. Okay, it means that first of all, this plus is a coproduct in a category, right? And this is a product in the category, categorical product. This is the terminal object in the category. Okay, but like descending from the categorical heaven, you know, most of the stuff is actually defined in sets. You know, so if we just think about a monoid as a set with some structure, well then this is a set. This is the carrier set, right? This monoid is a set. This is a product in the category of sets, so this is just a pair, right? So it's AA. Actually, maybe I should write it as M, because we usually call this type when we are defining a monoid, we call it M for monoid, right? This plus, well, it's, well, in Haskell we would write it as either, okay? Because it's a sum. Some coproduct is the sum type, so it's either, and one is unit. That's the singleton set, terminal object, singleton set, unit, right? So we could say that monoid, well, I don't know, F mon acting on M is this, right? Why is this a monoid? Well, because if you take an algebra for this thing, right? So an algebra for this thing would say, actually, maybe I should write it as an A and then specify it like an algebra is a choice of A, and we'll call it M now. Okay, it's like we pick a particular set, right? And we call it M, and it should be. An algebra would be, an evaluator would take Fm to M, right? That's an evaluator for this. So an evaluator takes a sum type, but a sum type, so we would have to like do pattern matching for a sum type, right? So it's actually two functions, right? One function, if you pattern match unit, right? So it would be a function that goes from unit to m. And the other function, if you pattern match on the second one, it would go from mm to m, right? So fm to m is actually a pair of functions, right? It's equivalent to a pair of functions. One function on a sum type is the same as a pair of functions. This corresponds to the case analysis, right? So these are the two functions, and we call this one well, not really this function, but we call this memty. It's equivalent to memty because it picks an element in M, right? So this is the unit element. And this one we call mapand. But really, mapand is kind of the curried version of this. It's M to M to M. But it's all the same, right? So I like this form because it's more general. The other one is more practical for programming. But they are totally equivalent. So, so this is when we define algebras using an endofunctor. The other way of defining algebras is by saying, well, these are operators. Okay, so this is more like a traditional understanding of algebra, where you have operators. You have multiplication, let's say addition, and stuff like this, right? So you have, this would be a binary operator. Takes two arguments of type m and produces m, right? This is a weird operator. We normally don't think of this as an operator, but it's a nullary operator, okay? We can, in an arbitrary algebra, we can have also unary operators, like going from m to m, right? So it's an operator that takes one argument. And for instance, we use this in groups. A group is just a monoid in which there is this inverse operation. So like, if it's a multiplication monoid, this will be like 1 over m, 1 over x, right? If it's an additive, it will be negative x, right? But it's a unary operator. We can also have, you know, ternary operators like this, and so on. So you can think of defining an algebra in a different way. You can either define it using this functor, or you can define it using operators. These two ways are almost equivalent, but functors are kind of more general. This kind of functors that you can write as operators, I mean, you can always take a bunch of operators and say, well, let me just combine them using some type and I'll get a functor, right? So from operators to functors, you can always go this way, right? It's always possible. But will you get all possible endofunctors? No. You'll get only polynomial endofunctors, right? Endofunctors that have this kind of polynomial as sum of powers. Okay? So today I want to talk about Lawvere theory. Of algebras, which actually talks about this kind of formulation when you start with operators. Okay? But this is not all. This is like half of the story. The second half of the story is the laws, right? These operators have to say, like, is this a monoid? Well, I don't know, because does this really pick a unit? I would have to check, right? If I pick this unit and then I multiply by something else, will I get this something else again, right? I don't know. Is it associative? I don't know. So we found out that in order to impose these laws, we actually have to go, I mean, either we can generate all category of algebras for this functor and say, and now we are imposing the laws, right? Or we can say, if we want these laws to be automatically imposed, then we have to go through this formulation where we started with a monad, right? A monad is also an endofunctor. So if we start with a monad and create monad algebras, which are special kind of algebras, right? And then these monad algebras, if they are compatible with the monad, they will automatically satisfy the laws. However, the monad is not this thing. This thing is not the monad that we're talking about. We're talking about the list monad. So in order to generate monoids with laws, we have to start with the list monad, which is a different endofunctor, right? It's actually list of A is like 1 plus A times X. No, 1 A L A, yeah. So it's a recursive definition, right? This is the definition of list. So it's a completely different approach. Now, in Lawvere theory, we go back to this endofunctor and we split it into these operators. But what Lawvere was interested in is, and that was his PhD thesis, I think, that he just came up with this whole theory. It's like a wonderful thesis. He said, I wanted to generalize all these algebras, not just monoid or like what is common for all these algebras? What is the structure that's common? So we would like to say, well, first of all, there is a category of monoids. There are lots of monoids, right? How do they differ? Well, they differ first of all by the choice of the carrier, right? So you can have a monoid based on just one element, or you can have a monoid that's like integers, right? You can have a monoid of strings, right? So they have different carriers. So every monoid corresponds to a different carrier, which we can think of as a set. Okay, so we have to pick a set. Plus, then there are these operators, right? So that there are these morphisms between these sets that will define operators, and there will be these morphisms that will define laws. The equalities between morphisms will define laws, and so on. What's the minimum thing that we need to be able to define all these monoids? So the idea is that if these are all these monoids, and they sit in set, right? We would like to have a category here that sort of is a template for all these monoids. Okay, so we'll call this category L-mon. So this is the Lawvere theory for monoids. And it sort of contains all the information that's common to all these monoids, all possible monoids. And we can get these monoids by mapping, by defining different functors from L-mon to set. Okay, so this is the idea. We'll call these models. A model is a functor from this category that's like a template for a monoid to an actual set. So this is like a much sparser category. It just has you know, a few structural things that make it into a template for a monoid, right? So what should this category contain? Well, it has to contain an object, I'll call it 1. And this functor will always map this object 1 into a particular set. This set will be the carrier of the particular monoid. So this will pick this M, right? This M, the carrier of the particular monoid, will be picked as the image of 1. Now this is an abstract category. This is not a set. This is just like an atom, right? Called 1. What else do we need? Well, we need an object that we will call 0. And this object will be mapped into this unit, okay? So unit is really, we can think of unit or the terminal object or the singleton set, we can think of it as the 0th power of m. So I'll call it m to the power of 0. Okay? So it's like if you take products of m, okay, m to the 0th is really the terminal object. Now we have to have object 2, which will map to m square. Okay? Or by m square, I mean this, right? This is my m square. Square in the sense of categorical product or Cartesian product, right? I will also need probably object 3 that will map it to m cube, right? And possibly more. Why would I need m cube? If I want to define a monoid, do I need all of these? I actually need the whole tower of power to define a monoid. Because I also have to define laws. And monoidal laws, for instance, associativity law. What does associativity law say? You start with 3 elements, right? And you multiply them differently. Like you first multiply the first 2 of them, and then multiply by the third. Or you multiply the second pair and multiply, right? So in order to formulate the laws, I also need m cube, because I have to have something that will start with 3 elements. Picking 3 elements means I have to pick an element of m cube. I might also need, I will actually need m to the 4th power and 5th power and so on. We normally don't talk about these higher order laws because they follow from the lower order laws. But there are laws that say, like, if you have A times B times C times D, right? In a monoid, right? What does this mean? Well, you can calculate it as AB times CD, or you can calculate it as like ABC times D, right? Like this, and so on. So there's like infinitely many of these laws that we don't even mention because they all follow from associativity law. But in principle, they sit there, okay? So the template for any monoid will have to have this tower of power, okay? It has to have these objects, at least these objects. And in fact, it's enough to have these objects 0, 1, 2, 3, and so on. Infinitely many of them, but corresponding to natural numbers, right? And they will pick the powers of m. They will pick an m and the powers of m. But in order for these to be really powers, okay, we'll have to have some kind of structure here that says this is a power